Friends, welcome to follow up this channel. So in this video, we are going to look at problem 1026, maximum difference between node and ancestor. So in this video, we are going to present some formats of solutions based on traversal. Actually, if you inspect the requirements for this problem is nothing but a binary tree traversal problem, right? And we just need to add some problem logic to the traversal algorithm. So meanwhile, this is today's daily challenge problem. And also we want to point out that we're not going to practice today's daily challenge problem. This is this one more precisely yesterday's daily challenge problem, right? So today's one is a very straightforward one. So with that said, our plan will be the following. First, we're going to digest the problem requirements, and then we look at the main point, and finally we look at the coding. So now let's look at the requirement. So here we are given a binary tree, right, rooted at the root node. So we want to find the maximum value v, for which there exist different nodes a and b, where v is the absolute value difference between the two nodes values. And here A is an ancestor of B, right? So here actually, because absolute value is symmetric, right? The A value minus B value is equal to B value minus A value in absolute value. Therefore, this condition, actually it's not symmetric, but we can interpret this one as seeing that A and B has a ancestor and offspring relation, right? That will be sufficient. So hopefully you can digest this sentence just now. So now a node A is an ancestor of B if either any children of A is equal to B or any children of A is an ancestor of B, right? So here we have two examples. In the first example, we see 0 and 3, right? And 0 is an ancestor of 3, and their difference is 3 in absolute value, so we return 3. So this is a very simple one. Well, if we look at example 1, so the return is 7. So you can check different pairs of such relations, or you can see 8 and 1, right? So 8 and 1, they have absolute difference 7. But if you look at 1 and 10, so their difference in absolute value is even larger, which is none, right? So, but 10 and 1 have no such relation, right? And 10 is not an ancestor of 1 and vice versa. So that's basically the two examples. So let's also look at the constraints. First, the number of nodes in the tree is in the range given by a closed interval, let's say 2 up to 5,000. And the node value is non-negative and bounded above by 10 to the power 5. So basically this problem size, I guess, is not a medium size or small size, I would say. So with that said, we are ready to look at the main point for this problem. Actually, if you want to solve this problem, it's the main observation is the following. So A is an ancestor of B, or B is an ancestor of A. So this statement is equivalent to that there exists a path containing A and B, right? If there are paths, there are two nodes, A and B. Either A is an ancestor of B or B is an ancestor of A. But as for computing this value, so we can just take this difference in absolute value, right? We don't care about the specific relation, whether A is an ancestor of B or B is an ancestor of A. That's the interpretation for this observation. So thus we can grasp the observation above. So we just need to do a traversal to compute the maximum difference, right? And then during the traversal, we can also update the difference and then return it after the traversal. So that's the overall logic. So now let's look at the coding. So for this problem, because solving this specific problem is not our goal. Our goal is to analyze it. So we can solve it and then we slightly change the code so that we can make connections with the vanilla traversal, right? And then where we want to spot where we add problem logic. So with that said, let's first do the coding. So here I'm going to initialize an answer. So this variable, so it's an attribute in this class. We're going to use this one to update the difference, right? So we're going to return its final state. Next, I'm going to define a function. Let's call it dfs, or just call it f. So here I have a node, and this a and b are the maximum value or minimum value so far, right? So I guess A, I want to say the min, and B, the max. So the node is a tree node, right? So we write like this just to make sure you understand the input. So what we want to return is the min and the max, including the current node. Right. So this way, because we are going to compute those maximum difference along a path, right? So you can understand that this is the current maximum difference up to this node inclusive. So with that said, let's look at coding. First, if not node, we just return, right? We don't do update. So if node, what we can do? So then including the current node, so we know the min and max will be node value and a, right? So max will be the node value and b, right? Then we are going to update this answer, right? So max self answer, and the difference between a and b. So because b is greater than a, so we use a minus b. So you can also use absolute value a minus b, right? But because here is min, here is max, b is no less than a. And then we do stem traversal for, say, left node, left subtree. So then the current maximum ending at before, I would say, before this node will be a, press a, and then b. Similarly, we do the same thing for node right, a and b, right? And then that's basically about it. So here I would say we don't do return, so we return none, but we update the self answer. So you can understand that this function is a worker, right? Do the thing. So with that said, what we do, we just need to call this function, right? So call it df. So originally we have a root, and then the press min, let's use float infinity. So here we use a positive infinity for minimum, because next time if we take min, we're going to take node value. So right. So then the latter one, we're going to use negative infinity, right? Then once you call this function, so this worker will do its job to update this answer, and then we're going to return it. This is actually advanced solution format. It's actually very short. So if you look at this code without the above analysis, it's not easy to see, oh, we are computing the difference, yeah, like this, because we didn't appear some specific path, right? But we just carry this information with this a and b during the traversal. If you do not add these two lines and then do the left traversal, right traversal, and then you first visit a node, it's binary tree traversal, right? But here is the problem logic, right? So let me problem logic. So now let's do a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So this is the one way. And then from solving the problem point of view, we make it. And then here we use this attribute to update this answer variable or attribute. So we can do similar thing, but with some slightly change, right? So here I want to introduce you to non-local variable, the non-local keywords. So here I can initialize this one, but I want to update this answer using this function, because the answer is not mutable, right? So this is not immutable. If I want to update it, I'm going to non-local this variable. So here, before I do things, first I'm going to do is non-local this answer. Therefore, so we are going to have this answer within this function as this answer have the same, I would say, the scope, right? That's the proper words. And then we do the same thing, but here I just delete this self answer. And then after we call this function, we just return the answer variable, right? So now let's do a test. Yeah, it passes one example. So now let's look at the generic case. Yeah, it passes all the generic cases. So now let me copy this function signature again, and then I will write another solution. So actually, for this problem, we can write quite a number of different formats of solutions. So the previous two versions are recursion based, right? So in this one, I'm going to write an iterative format. So for this is also very straightforward, right? So here we can use depth first based solution, or we can use breadth first based solution. Both are okay. So let me initialize a stack. When you see this stack data structure, so you actually should be able to interpret what I'm going to write is depth based. So initially the stack will save this root, right? And then the minimum, the maximum, and the minimum, right? So here I'm using this maximum. So we use float infinity. And here for minimum we use positive infinity. So here what we start are node and max and min, right? So basically this stack starts the min and max along the path before this root, right? So then let's do the traversal, and in between we are going to update the answer, right? So what we are going to do, let me also initialize an answer variable, and then because we do here we don't want to write nested function, so everything have the same scope as here. So we while stack, then I'm going to first get the node max so far and the min so far, right? So this is nothing but stack pop. So notice that here we use some something called unpacking, right? And then let's compute the min up to this root, right? The root or node variable more precisely. So then let's compute min so far. We're going to update that to be min of min so far, and also the node value, right? Actually the same thing as here, right? Then max so far will be the max of pre-state and node value. So this way you're going to include this node value information. In other words, we compute the maximum and min up to this node, and then we can update the answer variable. So the answer variable will be updated like this. So it's be max the pre-state, and then we want to compute this one, ABS min so far minus the node value, and ABS max so far minus the node value. The thought is that if for each node, we can compute this quantity or maximum difference and update it. After we do the traversal, we are going to get the full global information for the difference. So once we do this, then we are going to, so all those actually are problem logic, right? So also this two variable. If you just store a root and then do the following, it's just the vanilla traversal. Right? If node right, Then I'm going to stack append, say node right, then min so far, max so far. So I notice the order, max so far and min so far, right? If node left, so I'm going to copy this again, but I'm going to change this right, modify this right to be left, right? So now we are going to do the return answer. Let's do a quick test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. Here I want to make a comment. First, if we ignore the last two components in the tuple when we initialize the stack, and then we ignore also these three lines, and then we do this, check the right subtree, check left subtree. This is nothing but a pre-order traversal, right? So this is the one thing. But here you can do this two line, this three line, I would say, here, here, and here. So the problem logic, right? And then if you just ignore that and then just do the stack up or check right subtree, check left subtree, then you are going to get the vanilla traversal. But here in this problem or in traverse in this one, so the order of checking first the right subtree or first checking left subtree does not matter. But if you want to do pre-order traversal, you need to first check right subtree. So to verify this point, so each time you can print node value, right? So you can do the check. Then you are going to get let's see, 8, 3, 1. This is the pre-order traversal, right? 6, 4, 7, and 10, 14, 13. But if you put this one behind this one, for this problem, it also works, but it's no longer pre-order traversal. Let's check that. Right, so this is not pre-order traversal, but you know there's some symmetry here, and then we can comment this print, so we can test this. Will still pass all the test cases, right? So with that said, I guess that's basically about it for this video. Thank you.